Hey AP Calc, back for part 2 of this third lesson from section 1.3. All right, I've got two proofs that are, I would say, a level up from the kind of proofs we did last year, but everything that we do can be justified from this sheet right here. So I'm going to start with number 51 from the textbook. It kind of has a weird thing going on where it gives you 3u inside the parentheses, which means the angle is not a single angle, a double angle, it's a triple angle. And there's no triple angle formulas on this sheet anywhere. But what we notice is that whatever this is, it becomes a single angle in here and a single angle in there. So it's like those two thetas or the two u's, they're gone. The 3u, that's gone as well. So when you think about approaching this proof, I really wouldn't start on the right-hand side, because you can work with identities and you can try to do some algebra type stuff, but you're not going to be able to get to a 3 theta very easily, or a 3u. So this is what we got to do. We got to think to ourselves, is there a way in which I can break out of the 3u mold from the left-hand side? And there is, okay? If you scroll down to the bottom left corner of this, you got something called the sum and difference formulas. Which means if we were to separate 3u into two different pieces, like say, call it the sine of 2u plus u, right? 3 is 2 plus 1. I can do that. Then you can split it up to create the sine of 2u and the cosine of 2u. The sine of u and the cosine of u. All right, it's kind of weird because the formula given has u's and v's, and this is a u. I get it. That might be a little tricky. Check this out. Sine of u plus v is sine cos plus cos sine. So sine times cosine plus cosine times sine. So check that out. Make sure that you're piecing together like, oh, he split up the 3u, and now he's using the sum and difference formula. Those are sort of like the really tricky things that start this proof off. From there, though, we're kind of limited because the sine of 2u, like we're limited in the tasks that we can do. Sine of 2u is given a formula here, and there's only one version of it, so I'm just going to go for that right away. The sine of 2u is 2 sine of u cosine of u, and I'm just not going to put parentheses around the singles anymore. Right. And then cosine of 2u, that's a little trickier. I've got one version, two versions, 3 versions of it, and it's kind of difficult to decide which one's it's supposed to be right off the bat. So what I'm going to do is hold off on taking out, I'm just going to hold off on rewriting this. We'll just keep it. So 2 sine of u, we're now up to cosine squared of u, right? It's not cosine of 2u now. It's cosine squared because it's cos times cos. All right. And this is still the same. Now you notice, these are separate terms. They're separated by addition. So it's kind of like, you can start to think about things like factoring to see if that helps, especially since it seems like the sine of u was factored out of a quantity. They both have a sine of u. So I believe this is a sine that we should be factoring out the sine. So that's gone. That was a pretty weak pun. I don't know. Anyway. So now, how the heck are we supposed to show that 3 minus 4 sine squared is the same thing as a bunch of cosines? Well, I think the best move then would be to say that cosine squared does not belong at all. So we can use the identity where if I subtract sine squared from both sides, cosine squared equals 1 minus sine squared. So this becomes 1 minus sine squared of u times 2. Put a bracket here. Cosine of 2u then, this is pointing us exactly to which version we should use. This is the one version that only has sines. Let's put 1 minus sine, wait, what is it exactly? 1 minus 2 sine squared of u. And it's all still being multiplied by the sine of u. Although that sine of u is going to stay outside. Like, this one is not re-entering the conversation of inside because it belongs on the outside. All right. Wow, I'm just looking at this beforehand. 2 times 1 is 2, plus 3 is 3. 2 times negative sine squared u will be negative 2 minus 2. It's just algebra we need to do now to make the top version work. So I would say, what are the necessary steps to show once you kind of have figured out that it does work? Just show that this multiplies out. And then at that point you can say, combine like terms. I'm going to go back to parentheses because the brackets are no longer encapsulating groups of parentheses. Proof is over. We got it. All right, so sometimes the strategy is a little bit more involved than just the normal stuff that you guys learned last year, as is the case for number 53. For number 53, it says, show that cosine to the 4th power of theta divided by 2 is equal to 3/8 plus 1/2 cosine of theta plus 1/8 cosine of 2 theta. Now, you can search this formula, and there doesn't seem to be anything that would make a theta over 2, like there's no theta over 2 formulas in here at all. There doesn't seem to be, at least. No half-angle formulas. But right here, this has something. And the reason why this caught my eye is because we've got squared terms that seem to be doubling. Whatever's in here gets doubled when you put it out there. All right? And cosine to the 4th power is really like cosine squared squared. The reason why I want to double u to 2u is because I need to double 1/2 theta to get to theta. At least do that. So then the first thing I'm going to do is rewrite this as cosine squared of theta over 2. And just recognize, like, all right, we're talking about that quantity squared. Now, if we do that rewrite, we may now use this second formula within the power reducing formulas box. So they're saying that the u value is theta over 2 here. This will now be 1 plus cosine of double theta over 2, which gives me theta. Divide that by 2. And we're still squaring the quantity right there. Now this still seems like a long shot from where we need to be. I mean, we're talking 3/8 and 1/8 and stuff that just doesn't seem to be fitting at all right now. But we've got the square on the outside, which means perhaps we can like start squaring things. So if you take 1 plus cosine times itself, just make sure that you guys are expanding it properly. All right, 1 times 1 is 1, plus cosine. So there's a 2 cosine of theta in there, plus cosine squared. All of that's divided by 2 times 2. Yeah. So it seems as though breaking it into 3 different fractions might be a good idea, since there's 3 different fractions here. So you got 1/4 plus 1/2 cosine of theta plus 1/4 cosine squared of theta. You can still see all that? Very good. Now this is the point where you're like, I'm obsessed with the other side of the equation. I'm obsessed with trying to make it look like that. So we're good so far. Check that off the list. The middle term works. The last term is a cosine squared. We need a cosine of 2 theta. So the question is, how do I go from cosine squared to cosine of 2 theta? We just used it. Cosine squared of theta goes to cosine of 2 theta. So that's what we're going to do. We're going to do another power reducing formula where we replace the cosine squared with 1 plus cosine of 2 theta over 2. At which point, it's kind of just an algebra game now. One half plus cosine of 2 theta over 2 is being multiplied by a 4th. So I split up this fraction into 2 fractions. And then you can multiply the 1/4 through. So that would be 1/8. You know what? I'm running out of room, and I'm running out of time. So I'm going to rewrite it over here. And we're going to finish this. So you got 1/4 plus 1/2 cosine of theta plus 1/4. I'm rewriting that as 1 over 2 plus cosine 2 theta over 2. This then becomes 1/4 plus 1/2 cosine of theta plus 1/8 plus 1 cosine of 2 theta over 8, which makes perfect sense when you look at a statement that we're trying to prove. 1/8 plus 1/4 is the same as 2/8 plus 1/8. That's 3/8. So the 3/8 has come to light. 1/2 cosine of theta plus, there's the 1/8 cosine of 2 theta. All right. That was kind of tough.